Hello, hello, hello. In this worked example, we're going to calculate some of the probabilities that show up in the experimental tests of Bell's theorem when we use these entangled photon states. So in particular, the experiment that we're going to describe is one that we are actually doing down in the lab. We're creating a pair of entangled photons in this so-called Bell state, which is having equal probabilities of either getting both the signal and the idler photon to have horizontal polarizations when you measure, but there's also a 50% chance that if you make a measurement of the polarization, you will get vertically polarized results for both of the photons. Now, in this experiment, we're going to imagine that we have two different polarization analyzers, which we can rotate so that we're measuring with respect to different directions. So we're going to call PA theta sub s as a polarization analyzer that's going to analyze the signal photon with respect to the theta sub s direction. And when you do that, there's some probability that the signal photon will come out the theta sub s port, and there's another probability that it will come out theta sub s plus 90. And let's show how to calculate some of these probabilities. And the particular probability that I want to calculate is a type of joint probability. I want to calculate for a pair of photons that's in this entangled two-photon state here. What's the probability that when I make measurements, the signal photon will come out of this theta sub s port, and the idler photon will come out of the theta sub I port? So how do we calculate that probability? Well, of course, as usual, the way we're going to do it is to calculate a certain probability amplitude, which is an inner product that it looks like this, and then that's going to, in general, going to be a complex number, and then we're going to take the magnitude of that quantity and square it, and that's going to give us this joint probability. Okay, so to do this, we're going to start just by plugging in. Let's just calculate the probability amplitude, and then at the end, we're going to take the absolute value squared to get this joint probability. But the probability amplitude, we're going to start off just by plugging in for psi what the particular psi that we're considering in this case is. So we're just plugging that in here. And now here's the key step. When we go to evaluate, we have two probability amplitudes that we've got to evaluate. But each one is of a form that we've previously evaluated. When you have a situation in which, on the right-hand side here, the ket here involves just a direct product, a single direct product. So in that case, this probability amplitude looks like what we got when we were considering an unentangled particle, and we could just write this probability amplitude as the product of two one-particle probability amplitudes, like so. And then similarly, we can also write this probability amplitude as the product of two one-particle probability amplitudes, like so. And so our overall probability amplitude is just 1 over the square root of 2, and this first inner product here gives a factor of cosine theta sub s times cosine theta sub I plus 1 over the square root of 2 sine theta sub s times sine theta sub I. So taking this probability amplitude that we just calculated it, and taking the absolute value of that and squaring it, we conclude that the joint probability, theta sub s, the probability of obtaining the signal photon going out the theta sub s port and the idler photon going out the theta sub I port, is just 1/2 times cos theta sub s times cos theta sub I plus sine theta sub s times sine theta sub I, the whole thing squared. So this is an incredibly useful result because no matter what we dial our analyzers, our polarization analyzers to, no matter what angles we dial it to, this tells us what the probability of this joint event is of occurring. Now, if we want to make a connection with the experiment that's being described in the paper, is the moon there when nobody looks? The first situation we want to analyze is when both of these polarization analyzers are set to the same angle. And in this story here, that corresponds to both of these detectors being set to the same switch. And so what do we get? Well, we just plug in theta sub s is equal to theta sub I equal to some angle, which we'll just call theta. And what do we get? So apparently when the angles are set the same, when the switches are in the same position, half the time we will see both uh, the signal photon and the Euler photon come out of these ports. And half the time we won't. Half the time, maybe one of them will come out the port and the other one won't, or maybe they'll both come out different ports, but only half the time will they come out the same port. We're going to calculate this conditional probability given that the Idler photon comes out of this port. What's the probability that the signal photon comes out this port? In other words, what we're really going to end up asking is if you see, if the switches are in the same position, and if you see the green light flash here on this one, what's the probability that the green light on the other one will also flash? And it's a easily provable and perhaps familiar fact from ordinary classical probability theory that the conditional probability here is just calculated by taking the joint probability and dividing it by the probability p of theta sub I, where p of theta sub I is what fraction of the time, regardless of what's happening on the signal channel, what fraction of time will the Idler photon come out this port, and presumably the rest of the time it's coming out this port. Well, it turns out that the denominator here, it's easy to prove this, and I will in a second, but let me just tell you the result now. The denominator here is just a half, and the numerator we just showed is equal to 1/2 times cos theta sub s, cos theta sub I, plus sine theta sub s. Ran out of room there, so we could fix that. Sine theta sub s, sine theta sub I, this quantity in square brackets squared. And the 1/2s clearly cancel here. So this is our expression for the conditional probability, and it works for any particular values of these angles theta sub I and theta sub s. But we're interested in the particular case in which those angles are equal. So what we've shown is that when these angles are equal, the conditional probability is just cos squared theta plus sine squared theta, quantity squared, which is simply 1. And whoopsie, I should be writing the conditional probability, so I should have had a vertical bar here, so we can fix that. So that's exciting. What we've shown is one of the key observations that Merman talks about in this paper, and that is basically that whenever the switches on these two machines are set to the same position, it doesn't matter what that position is, but as long as they're the same, as long as you've got the same angle here, the probability of the signal photon coming out this port and, no, I'm sorry, the probability of the signal photon coming out this port, given that the idler photon came out this port, that probability is 1. And that's just another way of saying that if these switches are in the same position, the lights flash the same color. Or maybe a slightly more precise way of saying it is what we've shown is that if they're in the same position, if this one flashes green, the other one flashes green. And then, of course, it's not very hard to show that if you calculate the joint probability or rather the conditional probability, given that the idler photon comes out this port, there's a 100% probability that the signal photon will come out this port. And they will never come out different ports when the switches are in the same position. So we got all of that from quantum mechanics, and that's basically a prediction that quantum mechanics makes, which we can begin to test experimentally pretty easily down in the lab. Okay, and just one loose end to tie up in the above uh, derivation, I made the claim that the probability, regardless of what's happening with the signal photon, if you just send this entangled state in, what percentage of the time will the idler photon come out of this port? And I made the claim that it was equal to a half. Let's actually show how to calculate that using our probability amplitude method. Well, as always, we start off by saying that we're going to calculate this probability by taking the magnitude squared of the appropriate probability amplitude. So let's calculate that probability amplitude. So just plugging in what psi is, plugging in for psi here, and just taking the inner products, you see I get two inner products that we have to evaluate. And now we just have to look at this and say, what do we actually mean by this? We've got one state on the left side and a two photon state on the right side. It may not be entirely obvious what to do at this point, but do not despair. When we write these two photon states, it's understood that the quantity on the left refers to the state of the signal photon, and the quantity on the right corresponds to the state of the idler photon. And this one photon state, when we calculate this, it doesn't matter at all. It doesn't interact, so to speak, with the signal photon. It just can sort of pass right by that, and the appropriate thing to do at this point is to write this down as 1 over the square root of 2 like so. And so Beck actually explicitly puts in these subscripts to remind us that the first ket here has to do with the signal photon, and the second ket has to do with the idler photon. And we can do the same thing with this other term. I have 1 over the square root of 2, and now I'm going to have a V associated with the signal photon, and then this inner product of theta sub I times H associated with the idler photon. Whoops, this should clearly be a V here. And these one particle probability amplitudes, these inner products, you know exactly how to evaluate them. This gives a factor of cos theta sub I here, and then I have a 1 over the square root of 2 V sub S sine theta sub I. Okay, and now when we go to calculate the probability, when we want to take the magnitude squared, one way to do that is to remember that the magnitude squared of a complex number is that inner product times the complex conjugate of the inner product, like so. And then I can rewrite this as theta sub I psi. And then taking the complex conjugate here, it's the same thing as reversing the bras and the kets. So putting it all together, the probability that we're trying to calculate, I can write as just, there's going to be a 1 over the square root of 2 of, and now I'm going to write out the bra side. It's cos theta sub I h, and I guess Beck puts the subscripts on the left-hand side when they're bras here, plus sine theta sub I with the V, and that whole thing times 1 over the square root of 2 HS. Whoops, let's back that up. Let's put the cosine theta I term first, HS plus 1 over the square root of 2 sine theta sub I V sub S, like so. Well, it's pretty easy to see what's going to happen here. First of all, there's a factor of 1 over the square root of 2 times 1 over the square root of 2, so that's going to give a factor of a half. And then due to the orthonormality of these h's and v's, you're just going to end up with a cosine squared term and a sine squared term surviving. So putting it all together, what do we get? We get that the probability of the idler photon coming out the theta sub I port is 1/2 times 1, or 1/2, which is what we set out to prove. So there you have it. Okay, so those are examples of how to work out these probabilities. It's a little bit messy and potentially confusing. I know I always get a little bit confused when I do these probability calculations. There are lots of examples of these done in Chapter 8 in Beck. There are a number of them that you're going to do for the problem set, so you'll get lots of practice. So that's it for this worked example. Hope to see you again soon. Bye-bye.